Solids, liquids, gases. Those are the main phases that all matter has. So what about the transition of going from one to the other? This is what we call state transitions or phase transition. And so it's how the compound goes from a solid to a liquid to a gas, or going backwards from a gas to a liquid and a solid. And we're also going to talk about going from a gas to a solid or solid to a gas as well. So to start thinking about this, well, let's start with a pot of water. And in this pot of water, or I should say pot, we're going to have ice, solid water. When we have this pot on a stove, we're going to put heat into it. And so what's going to happen eventually is those solid particles will start getting more and more energy from the burner of the stove. And they're going to start increasing in energy, getting faster and faster, and eventually they're going to break that crystalline structure and form a liquid. Then all the energy is going to go into the liquid, and those liquid molecules are going to start moving faster and faster and faster. Eventually they're going to be spread apart. Then that's when they become a gas. So we have these terms that we have for going from a solid to a liquid to a gas. And so let's talk about what that terminology is. So going from a solid to a liquid, well, we call that melting. So going from a solid to a liquid is melting. And what I'm going to do is kind of show that with how the change in temperature is going to be affected. So I'm going to have my blue pen kind of start it off, because we're going to start pretty cold for the solid and then more energy going to the liquid. And so it takes a lot more energy. These liquid molecules have a lot more energy in them than the solid molecules. And so we call this, going from a solid to a liquid, we call it melting. Now, what about going from a liquid to a gas? Again, the liquid has a much lower temperature than the gas does. And so we're going to start off with a cooler temperature. And then eventually we get to the warmer temperature. And that right there, when we go from a liquid to a gas, we call that evaporation. So going from a solid to a liquid is melting, and liquid to a gas is evaporation. Now what about going in the other direction? Let's say we have a gas and we want to cool it off into the liquid phase. Well, when that happens, we call that condensation. So going from a warmer component to a cooler component, going from the gas to the liquid, this is what we call condensation. We're basically condensing the gas into liquid. And then going from the liquid, which again is going to be the warmer part, and then going to the solid, which is a little bit cooler, is what we call freezing. Let me use that as, make this the black. So going from the gas phase to the liquid phase is condensation. Liquid phase to the solid phase is freezing. Now, many different compounds have different points where they melt and freeze or condense or evaporate. Before we get into the differences in those temperatures, let's first talk about what is the difference between melting and freezing. Well, melting and freezing all occur at the same temperature. In the case of water, it's at 0 degrees Celsius. So liquid water will freeze to ice at 0 degrees, and the ice will melt into liquid at 0 degrees. The liquid will boil or evaporate into a gas at 100 degrees C, and it will go from the gas phase to the liquid phase also at 100 degrees C. So melting and freezing happens at the same temperature. Condensation and evaporation also happens at the same temperature. The big difference between this is that, let's say we will go from the liquid phase to the solid phase. The liquid phase has more energy than the solid phase. The solid phase has less energy than the liquid phase. We're getting more energy going to the liquid. And then also going from the liquid phase to the gas phase, we're getting more energy. The gas molecules will end up having more energy than the liquid molecules, or vice versa, where the gas molecules have will lose its energy to go to the liquid phase. And so here, going from a solid to a liquid, we are gaining energy. Going from a liquid to a gas is requiring energy. Going from a gas to a liquid gives off energy. Liquid to a solid also gives off energy. Now, what about the melting and freezing point of different compounds? How is that temperature different? Well, those temperatures are basically based off of intermolecular forces. So whether or not the compound is a polar or nonpolar compound, if it is a polar compound, then it's going to require more energy to separate out those molecules, because that polarity is keeping it together, the dipole-dipole interaction. So if there's hydrogen bonding present, it's going to require even more energy. And so the melting point or freezing point actually is much higher for compounds that have hydrogen bonding than dipole-dipole interactions, which again is higher than ones that just have dispersion forces. So the types of intermolecular forces are important to determine kind of how high, what the relative temperatures are of melting and freezing. However, the intermolecular forces are not the only things that play a role in what that temperature is. Also, the size of the compound plays a role. And the size is dependent. When the greater the size, the larger the molecule is, the more dispersion forces that it has. And so the larger molecules have a higher melting point or freezing point than the smaller molecules. And that has to do with the dispersion forces. Now, what about boiling point and what boiling is? So what is boiling? Well, boiling is a form of evaporation. So evaporation is going from the liquid phase to the gas phase. Well, for water, that doesn't only happen at 100 degrees Celsius. I mean, imagine we just had a rainstorm. The rain falls down, forms puddles on the sidewalks, your deck, on your driveway. There's puddles everywhere. Well, it's springtime, so the temperature is usually maybe 70, maybe 80 degrees Fahrenheit. And so after about an hour or two, those puddles just kind of disappear. So did the water boil? Did the water reach 100 degrees C or 212 Fahrenheit to go from the liquid phase to the gas phase? No, it did not. The water was at whatever the ambient temperature of the environment was. In the case, it was 70 degrees. So how did the water go from liquid phase to a gas phase? So this is where we need to start thinking about what's actually happening in the molecules. Let's dig down deep and picture in our minds what the molecules are actually doing. So the molecules in water are always moving. They're constantly moving around. And so a puddle has lots of surface area. And so those water molecules are moving around. So you can imagine that some of those molecules can have just enough energy and the right direction where they end up zipping right off of the surface. They go past the surface and into the gas phase. Not all the water molecules do it all at once, but some of them do. So over time, more and more water molecules will end up leaving the liquid phase and going into the gas phase. And if it's outside in an environment, those gas molecules float off into the air. Now, if we had a closed container, then that doesn't really happen. And so you see that a lot of times in the summer when you have a water bottle, it's sitting outside maybe half full, 3/4 full, and over time you end up seeing droplets of water on the inside. And so what's happening there is the water is evaporating, but it doesn't have anywhere to go because we have closed off the container. But so those water droplets then hit the sides of the wall, and rather than going anywhere, they cool off because the container wall is colder. And so when it hits the side of the wall, it transfers some of its energy to the wall, slows down, cools off, and then ends up getting attracted to any other molecules that are really close by and condensing into liquid. And so you end up with little droplets of water on the walls of the container. And so this happens at all temperatures because those water molecules or any molecules are always constantly moving, and so some are always leaving the liquid phase and going into the gas phase. Now, that is what we call evaporation, going from a liquid phase to the gas phase, and then going from the gas phase to the liquid phase, like I said, is condensation. Now, what about going from the gas to a solid? So, before I get to gas and solid, let's go from solid to gas. Going from a solid to gas is what we call sublimation. And so, again, let's use the colors. We'll start with blue here because the solid is going to be lower in temperature. And then we're going to go to the gas phase. And so this right here is what we call sublimation. So when things sublime, going from the solid phase to the gas phase, they're just completely bypassing the liquid phase. So what are some examples of things that have sublime that you're probably familiar with? Well, one thing is air freshener. If you have a solid air freshener, then over time that solid will disappear and eventually fill the room with pleasant smelling things, compounds, so it smells good. And so what's happening there is the solid is subliming into the gas phase. Another example you might have come across are ice cubes. Ice sublimes. So if you have a freezer and you have really old ice, you might notice that a lot of the ice cubes are just really, really small. Well, how did they get small? They're small because the water sublimed. It went from the solid ice to vapor, to water vapor. And so that is what we call sublimation. Now, what's the opposite of sublimation? What if we go from the gas phase to the solid phase? So in the gas phase, we're much higher in energy, and then we cool off into the solid phase. And so going this way is what we call deposition. The gas is depositing as a solid, and so we call this deposition. So you're familiar with this, or you might have seen this in the winter time in terms of frost. When it's really cold outside, there's air in the water vapor in the air. It hits the cold windshield on your car, and when it hits the cold windshield, it condenses. I should say it deposits into ice crystals. And so we go from the gas vapor to solid ice. And so that is deposition. And so frost is an example of deposition. All right, let's go back to evaporation. Let's talk a little bit more about evaporation. So as I said earlier, evaporation can happen at any temperature. And so when we go from the liquid phase to the gas phase, vapor is being created. And you can imagine that vapor, those liquid molecules are escaping into the gas phase, and that's causing a pressure above the liquid because the gas molecules are escaping, they're pushing out, and it forms a pressure. Remember, pressure is a force per area, and so that force was the molecules actually escaping the liquid phase. And so a pressure ends up getting established. We call that a vapor pressure. Some compounds have a very high vapor pressure, and that means that the molecules really quickly escape. They evaporate very quickly. An example of something that has really high vapor pressure would be like nail polish remover. If you spill some nail polish remover on a tabletop, you could see that it pretty much really quickly evaporates away. And so that's because those molecules that make up the nail polish remover have a very high vapor pressure. All those molecules are just escaping into the gas phase. There's nothing trapping it, and so they're never condensing back down. So as these molecules are escaping into the gas phase, there comes a point where as the temperature increases, more and more molecules end up escaping into the gas phase. And as the temperature increases, the vapor pressure is going to increase. So what prevents liquids from just instantly boiling? That is the atmospheric pressure. The atmospheric pressure is constantly pushing down on the liquid, keeping that vapor, causing that vapor to go back into the liquid phase. And so that atmospheric pressure is pushing down on the vapor, causing the vapor to go back condense. And then the liquid goes and evaporates and becomes vapor again. And so an equilibrium kind of gets established where the same number leaves as goes in. Well, when the vapor pressure actually meets and matches the atmospheric pressure, when those two pressures are equal, we have what we call boiling. And so the boiling point of a liquid is when the vapor pressure of a liquid equals whatever the external pressure is, which is usually whatever the pressure is of wherever you are. And a practical example of this is high altitude cooking. In Colorado, Denver, Colorado, the mile high city, the atmospheric pressure is really low. It's not one atmosphere like it is at a beach, like in Florida or in Texas. At the beaches there, the atmospheric pressure is one atmosphere. In Colorado, it is much less. And so in Colorado, we don't have to have as much energy for those liquid molecules to escape to go into the gas phase. So since we don't have to have as much energy, the temperature is not as high. Because remember, temperature and energy are proportional. As the temperature goes up, the kinetic energy goes up. So the molecules don't have to have as much kinetic energy to increase the vapor pressure to match the atmospheric pressure. And because of that, water boils at a much lower temperature in Colorado than it does pretty much elsewhere. And so that has to be taken into account when you're cooking, because things have to cook a lot longer because you don't have as high of a temperature. Now, we can kind of graph how the temperature changes as we add more and more energy to a substance. And so let's look at how that changes. If we kind of make a graph here where the y-axis is our temperature and then our x-axis is energy. And so we're going to constantly be increasing the energy. And so let's start off with ice. So we have some ice at some temperature, and so we know that ice melts at 0 degrees C. So let's go ahead and put 0 degrees right here. 0 degrees C is right there. And so we have some ice that's well below that. We're going to start maybe right there. And as we increase the energy, as the energy goes up, what happens to the temperature? Well, as you put more and more energy into it, those molecules are going to start moving more and more. So therefore the temperature's got to go up. And so the temperature is going to increase. And it's going to stay constantly increasing. If we have a constant amount of energy, the temperature is going to steadily increase until it hits that 0 degree mark. At 0 degrees, what's going to happen is the temperature is going to level off. And so it's going to look like we're going to keep putting energy into it, into this ice, but there's not going to be a temperature increase. So where is all that energy going? Well, this is what we call a hidden energy, because we can't really see what the energy is doing. It's not being shown with a temperature increase. This hidden energy is going into the actual molecule itself. It's going into the potential energy of the molecule. And so those molecules, in the case of water, the water molecules have hydrogen bonding that's keeping those water molecules close together. And that hydrogen bonding, the energy is going in to separate out that hydrogen bonding, to overcome the hydrogen bonding. So it is kind of separating out the molecules so that they can start moving around. And so there's a plateau that actually happens at 0 degrees C where melting is happening. And so when ice is melting, it doesn't matter how much ice is in there, if there's liquid water and solid water, it's going to be 0 degrees C, because all the energy that goes into it is going to go into changing the phase of the solid into the liquid. And so this becomes what we call a phase change. So this right here is where melting is occurring. And so eventually though, all that ice, all those solid particles, those solid molecules will be far enough away where now everything is a liquid. And so at that point, when we start putting more energy into it, we start getting another temperature. So we're going to keep putting energy into it. Temperature is going to go up, up, up. And then eventually, when we hit 100 degrees, we're going to have boiling that's going to happen. At 100 degrees C, the liquid goes into the gas phase. Now, when that occurs, it's going to level off again. And again, it levels off for the same reason as it leveled off here. All the energy now, those liquid molecules, all the energy is going into those liquid molecules to separate the liquid molecules into the gas phase, because it takes energy to overcome that hydrogen bonding. And so that is energy that's going into the potential energy rather than the kinetic energy of the molecules. And so this is where boiling occurs. Once all those liquid molecules are far enough away and now are gas, we start getting another increase in temperature, and the temperature actually increasing forever as you increase the energy. And so this right here is what we call a heating curve. And in this case, this is a heating curve for ice or for water. And so as here we have solid, this is liquid right here where we start increasing, and then this right part is our gas. This is where we have melting, and this is where it's boiling or evaporating. So it starts out as a solid, it melts into a liquid, and then evaporates into a gas. And so this is what we call a heating curve. We could do the same thing going backwards. Going backwards would be a cooling curve. So we start off with a gas, we cool it off, it condenses into a liquid, and so forth. And so that is what we would call a cooling curve.